This is the third video on thermodynamics. We start with the first law of thermodynamics. Now, what is the first law? The first law of thermodynamics, I've written in short, big spelling, so I've written in short TD, is nothing but energy conservation applied to a thermodynamic system. I have already discussed about the thermodynamic systems in the previous videos. We have to remember that first law is nothing but energy conservation. Conversion of heat into work and work into heat, interconvertibility. When a system takes some amount of heat from its surroundings, it is used up in two ways. I repeat, when a system takes some amount of heat from its surroundings, it accepts heat from the surroundings, then this amount of heat is utilized in two ways or used up in two ways. Number one case, a part of a part of it increases the internal energy of the system. Second is the remaining part is converted to some external work done by the system. So it is used up in two ways. First one is a part of it increases the internal energy of the system. We have to discuss this term in greater detail. The remaining part is converted to some external work, or you can say useful work done by the system. System has done some work. Energy has been expended to perform that work by the system. Always remember this word, by the system. So we can say that heat absorbed is equal to rise in internal energy plus external work done. I repeat, heat absorbed is equal to rise in internal energy plus external work done. Now, this gross statement that we have studied from the first line is the general statement of the first law of thermodynamics. Now, first law of thermodynamics, as we have said, is the energy conservation law. The first law of thermodynamics is in essence the energy conservation law, and which is applicable to every thermodynamic system together with its surroundings. I repeat, it is applicable to all thermodynamic systems, every thermodynamic system together with its surroundings. Now, if we try to write the equation in mathematical form, then we need three or four terms. We write Q as the total amount of heat. Total amount of heat from the surroundings that the system has absorbed, let it be Q. There is a change in internal energy, that means UF minus UI. Internal energy is represented by U. UF is the final internal energy and UI is the initial internal energy. That means some part of internal energy, if absorbed by the body, then there will be a rise in the temperature of the body. So UF minus UI denotes the change in internal energy of the body. As I have said, heat absorption by the body rises its internal energy, plus remaining part is converted into external work. So we write W here. So these are the two parts. I had first mentioned that increases the internal energy. This is the first part, and the remaining part converted to some external work is the second part. Now we try to find out the relation between the Joule's law of mechanical equivalent of heat that we had done in the previous video, that is W is equal to JH. The formula was W is equal to JH. I started with this. So Joule's law of mechanical equivalent of heat and the first law of thermodynamics. What is the relation between these two? Now we can say that Joule's law of mechanical equivalent of heat is a special case of the first law of thermodynamics. That is a special case. Now, if we take W is equal to JH, here we will apply Q instead of H, because we had said amount of heat absorbed from the surroundings was Q. So the relation is W is equal to JQ. W is equal to JQ. W you can write also H also. W and Q are expressed in the same unit. W and Q are expressed in the same unit. So Joule's equivalent J is equal to 1. W, Q are in same unit. Therefore, J is equal to 1. Now, when the internal energy of a system does not change, UF is equal to UI. If internal energy that means therefore we can write Q is equal to W. Here we will write the differential form of the first law of the thermodynamics. We have written in the previous page that Q is equal to UF minus UI plus W. Now we can write dq is equal to du plus dw, suppose. So this is the differential form of the first law. That means change in the original amount of heat supplied to a system is utilized in two ways. One is the increase in, or rather here denoted by a change du, increase in internal energy, and another there's an increase in the system does external work. So this energy is utilized in two ways. Now this is known as the differential form of the first law of thermodynamics, whereas the equation Q is equal to UF minus UI plus W is known as its integral form. Now when is dq taken positive? When is dq taken positive? dq is taken positive when heat is absorbed by the system. Heat absorbed by system, and dq taken negative dq is taken as negative when heat is released from the system. Significance of internal energy. Now what is internal energy? The stored energy inside the body is known as the internal energy. You can give an example. Whatever internal energy we have comes from the food we eat. Now from the first law of thermodynamics, it is known that mechanical energy can be converted into heat and vice versa. Certain amounts of heat is required to do a certain amount of work. On the other hand, certain amount of work has to be done to generate a certain amount of heat. That means heat converted to work and work is converted to heat. Now the term internal energy, you can say that in different thermodynamic process, if we take only work and heat as the two manifestations of energy, the conservation of energy principle is violated. However, every body under every state has some internal energy, and if we consider the change of this internal energy along with heat and work, energy remains conserved in all the cases. During transformation from one state of the body to another, the change of internal energy does not depend on the intermediate path. So we can write one point: change of internal energy does not depend on path, or rather intermediate path. The change of internal energy does not depend on the intermediate path. In thermodynamics, there is no need to identify the source of the internal energy, but it is seen that from kinetic theory of gases, this chapter we are going to discuss in the uh, next chapter, next class. uh, Kinetic energy and the potential energy due to translational, rotational, and vibrational motions of the molecules of a body are the sources of internal energy. I repeat, this point is very important. It is seen from kinetic theory of gases that the kinetic energy and the potential energy due to translation, rotational, and vibrational motions of the molecules of a body are the sources of its internal energy. Now, another important term, perpetual motion. Now, what is perpetual motion? Uh, if you try to explain what is perpetual motion, the first thing that we must learn that perpetual motion does not exist in nature. Perpetual motion is of two or three kinds. The first kind, I'm saying, does not exist in nature. Now, what is perpetual motion? We all know that it is completely impossible to get work without dissipation of energy. That means energy gets converted to work, but it is an impossible case to get work without dissipation of energy. It is impossible to invent a machine which can work indefinitely without any supply of energy. The machine is working, but there is no supply of energy. This is absolutely or practically not possible. Now, if a machine can work indefinitely without any energy input, its motion is called the perpetual motion of the first kind. So, perpetual motion means if a machine can work indefinitely without any energy input, its motion is called perpetual motion of the first kind. But as we have learned from the first law of thermodynamics, which expresses that the law of conservation of energy states that this is impossible. Perpetual motion of the first kind is impossible or does not exist in nature. So I have written the important lines for you that if a machine can work indefinitely without any energy input, its motion is called perpetual motion of the first kind. Perpetual motion of first kind does not exist in nature. It is a completely impossible case. Now another topic, origin of internal energy. From where do we get this internal energy? Now, suppose from the first law, we say that for complete conversion between W and Q, uh, we have UF is equal to UI. First, let me write dq is equal to du plus dw. For complete conversion between W and Q, we need to see that du is equal to 0. If du is equal to 0, then UF minus UI is equal to 0. That is, the internal energy of a system does not change. Internal energy UF is equal to UI. So, internal energy does not change. But complete conversion between W and Q is an ideal case. W and Q conversion is an ideal case. Directly from the law of conservation of energy, we get the existence of a new thermodynamic property, that is the internal energy U of the system. Internal energy U of the system. For example, when a system takes some heat from outside but does no work, it takes heat but it does no work. So what happens? There is an increase in internal energy. So the effect of heat on a system doing no work is a change in its internal energy. These effects are a rise in temperature. As I've already said, that the measure of internal energy can be done by a temperature or a thermometer. That means more the temperature of the body, more is its stored internal energy. These effects are rise in temperature, melting of solid, vaporization of liquid, etc. These are examples where the change of temperature of the system or the change in latent heat gives a measure of the change in internal energy. One or the other forms must be given so that heat can be supplied to the system. Now, internal energy of a gas. What happens in internal energy of a gas? thermal condition of a fixed mass of gas is determined by three quantities. Number one, temperature. Number two, pressure. And number three is volume. But internal energy of a gas does not depend on all of these three quantities. It depends only on its temperature. In some cases, you can see that there is no change in internal energy if the pressure or volume at pressure and volume of a monoatomic ideal gas of a particular mass changes at constant temperature. Now, if we know the rise in temperature of this type of a gas, we can determine the increase in internal energy. But the change in internal energy does not always depend on the change in temperature. If a gas undergoes phase change, there is no change in temperature, but its internal energy changes. Internal energy will always change at first. Now, this is a very important question. Limitations of the first law of thermodynamics. Number one, the rule goes as the heat can flow only from higher to lower temperature and never from lower to higher temperature. Number two, some amount of work can entirely be converted into heat, but complete conversion of heat into work never occurs in nature. So, the maximum heat or work available from a certain amount of work or heat, irrespective, cannot be determined from the first law of thermodynamics. So, the first one is heat can flow only from higher to lower. So heat can flow only from higher to lower temperature. We write temperature here also. And never from lower to higher. Number two was some amount of work can entirely be converted into heat. Entirely can be entirely converted